Structural design is a fundamental aspect in constructing strong and safe buildings. In this video, we'll walk you through the basics of structural design for beginners, covering topics such as beam layout, load calculations, various techniques, and the relevant standards. The example shown in this clip is a two-story residential house with a floor plan of 6 by 9 meters. Let's begin by defining the units of measurement. In this video, distances will be measured in meters, cross-sectional dimensions in centimeters, material strength in KSC, and weight in kilograms. Feel free to adjust the units according to your specific preferences or standards. In this video, we'll walk you through the Pro mode to explore all the app's design features, including tools for construction workflows and cost estimation. Start by creating a new project. Name the model. In the Elevation field, enter the beam top elevation for that floor. For example, the beam top elevation for the first floor is at plus 0.4 meters. If you're unsure why the beam top elevation for the first floor is set to plus 0.4 meters, we'll explain this further in the step where we define the floor type. In the Wind Load field, if wind load data is not available, use the following default value. For the first floor, with a height not exceeding 10 meters and not located in a high wind zone, assume a wind load of 60 kilograms per square meter. Note that this guideline may not apply in some countries, so be sure to verify local regulations before using this value. Beam layout technique. Step 1. Place the beams along all the column axes. Start by entering the span distance. For example, begin drawing a beam from grid line A1 to A2 with a span of 3.5 meters and select the upward direction. Start by placing the beams along the outer columns to create the grid lines. Once the outer columns are placed, the program will automatically generate the grid lines along the column axes. If you need to draw a beam to the next grid line, there's no need to input a new span. Simply drag in the desired direction, and the beam will be placed along that grid line automatically. The advantage of placing beams along all column axes is that it helps prevent excessive column slenderness, ensuring better stability. Beams cannot be placed along the column axis at the plus 0.4 meter level for grid lines C1 to C2 and B1 to C1 because the floor level is set at plus 0.0 meters. Therefore, we will create a new level at plus 0.0 meters. Click on the map icon and select the plus button. Enter the elevation of 0 meters and keep the same wind load. Then, go back to the first floor to select the reference point. Once back at the original level, enter the span of 3.5 meters and choose the downward direction. This will place the beam along the grid lines C1 and C2. As for the beam between B1 and C1, it's not recommended to place it if the car park floor is designed as a slab on grade, as the car park floor will settle faster than the house foundation and may cause the beams to fail. Therefore, avoid placing beams over the slab on grade car park. Step 2. Every wall position must have a beam to support it, since precast floors cannot bear the load of the walls. And the same applies to cast-in-place floors unless you design the floor to support the wall load. However, in this example, we will not go into that detail. Start by canceling the beam at both the starting and ending points. For the positions where you need to place a secondary beam, move 1.1 meters to the left. Enter the distance and choose the direction to the left, then drag downwards. For grid line A1, there will be a 1 meter overhang. Enter the length as 1 meter, select the direction to the left, swipe upward, and then swipe to the right. In the case of the bathroom, there are two options. Use a cantilever beam, or add a column below and transfer the load to the ground level beam. In this example, we will use option 2. Enter the distance of 1.5 meters. Make the last position a column and select the downward direction. Step 3. Place the stair support beam. Select the position at grid line B3, set the offset to 0.5 meters, choose the direction to the right, and swipe downward. To create the second floor, start by copying the beam layout from the first floor. Click the Copy button. The beam top elevation for the second floor will be set at 3.75 meters. Double-click to switch modes. In this mode, you can copy the selected beam span and delete the selected beam. Select and remove any unnecessary beams. The beam along grid line C2 to C3 corresponds to a landing, so cut it out and create a new level at the same elevation as the landing. The landing elevation, according to the design, is plus 2.2 meters. Go back to the second floor. Select the reference point at grid line C3, enter the span of 2.4 meters, and choose the downward direction. Return to the second floor and draw the beam along the wall. For grid line 4, we will design it as a cantilever slab extending 0.5 meters. At grid line B3, a cantilever beam will be extended from the main beam. When designing cantilevered slabs or beams supported by a main beam, specific safety guidelines must be followed. First, a cantilever beam supported by a main beam must be anchored with a back tie beam to reduce the torsional forces on the main beam. Exceptions can be made if the cantilever beam has a short span and low loads, such as beams used for service openings or those supporting non-structural walls. In such cases, a back tie beam may not be necessary. The software will calculate the resulting torsional forces and ensure they are within acceptable limits. For safety, designers must adhere strictly to these recommendations. Next, we will focus on the roof beams. We will copy the beams from the second floor as well. According to the roof plan, the elevation is at plus 7 meters, and the wind load remains at 60 kilograms per square meter since the height is still under 10 meters, as per the requirements. Remove any unnecessary beams. For the roof structure, the beams to be placed are those along the column axes and the beams supporting the roof framework. In this case, we are drawing concrete beams. If it were steel beams, we will show how to create them during the roof modeling step. To delete a floor that is no longer needed in iOS, swipe left to delete. On Android, tap the trash can icon. Once the beams are placed, move on to the next step, selecting the floor type. Before entering the floor live load, let's first review the minimum live load requirements. In this example, since it's a residential building, we'll choose the second option, 200 kg per square meter. As the house doesn't have any special heavy loads, we'll use the minimum value as specified. Enter 200 in the live load field. For the next field, the dead load on the plank slab must include the weight of the slab itself. Generally, for residential buildings, the plank slab has a thickness of 0.1 meters, and the length of the slab should not exceed 4 meters. If the span exceeds 4 meters, we will add intermediate beams to support it, as shown in the diagram. Therefore, for the plank slab, we use a load value of 240 kilograms per square meter for the slab and 60 kilograms per square meter for the tiles, which totals 300 kilograms per square meter. Next, select the floor type. The plank slab will transfer the load in the direction we choose, and we can select the orientation based on our judgment and experience. The program will then distribute the load in the selected direction and design it to ensure safety. For the bathroom floor, we will design it as a cast-in-place slab due to the following reasons. 1. The bathroom floor will have openings for pipes, and precast slabs cannot have holes drilled, making them unsuitable for this purpose. 2. Water leakage issues. Precast slabs are not capable of preventing water leakage effectively. 3. A cast-in-place slab can be poured at different levels, and since the bathroom floor is typically lower than the exterior floor level, a cast-in-place design is more suitable. Regarding the weight of the cast-in-place floor, there's no need to consider the weight of the slab itself, as the program will automatically include it in the design process. Therefore, the weight to be used is the weight of the floor tile, 50 kg per square meter, plus the topping layer weight, which may be added to adjust the floor level. We'll allow for 250 kg per square meter for the topping, bringing the total to 300 kg per square meter, which is equivalent to the weight of a precast plank slab. The reason we set the beam top elevation at plus 0.4 meters is that the plank slab is placed on the beams, which means the floor level will be at 0.4 meters plus the 0.1 meter thickness of the slab, resulting in a floor level of 0.5 meters as indicated in the plan. Select the floor type for the second level and follow the same process as for the first level. If you need to modify the beam layout, you can return to the main screen. The previously entered data will not be lost, and you can continue adding the floor later. Once the floor layout is complete, there will only be a cantilever slab at grid line 4. Remember, whenever there is a cantilever slab or cantilever beam, always check for these precautions for safety. The second point is that the cantilever slab connected to the beam will create a torsional force on the beam. The solution is to cast the slab on the opposite side of the cantilever, as shown in the image. However, there is an exception for cantilevers. If the cantilever is small and the load applied is minimal, it can be done. For residential buildings, the recommended maximum cantilever length is 0.5 meters. In this example, the cantilever slab is 0.5 meters, so we will not cast the slab on the opposite side. To create the cantilever slab, select the Draw Cantilever Slab button. Set the reference point, enter the span in the x-axis, horizontal, and y-axis, vertical directions, and choose the direction for each axis. Finally, input the load in the same way as for the cast-in-place slab. For this level, there is no roof slab, so set the slab option to None. Once the floor is placed, the remaining functions will be added automatically. The next step is to input the load on the beams or the wall load. Let's go to the wall load input page. Before entering the load, let's first review the weight values for different wall materials. Currently, lightweight concrete blocks are commonly used for walls, but designers often use the weight of red bricks for all types of walls. If you prefer to use the actual weight, that's fine as well. We will share all images and information in this video on the Facebook page, AutoRC Analysis and Design, and the link will be in the description below. In this example, we'll use the weight of half-sized red bricks at 200 kilograms per square meter. This weight must be multiplied by the wall height before entering it into the program. To calculate the wall height, subtract the elevation of the current floor from the next floor level, 3.75 meters minus 0.4 meters, which gives 3.35 meters. We'll estimate the beam depth as 0.35 meters. This gives us a total height of 3 meters. So, the wall weight to use is 200 multiplied by 3, which equals 600 kilograms per meter. Start by selecting all beams that support half-height masonry walls and assign a load of 600. Then, click OK. Next, select the beams supporting full-height masonry walls and assign a load twice that of the half-height walls, which is 1200. For walls that do not fully span the beam, select the beam and use the sliders to adjust the position as needed. To move the wall to the right, adjust the upper slider. Observe the orange indicators on the plan, as they will show the exact location where the load will be applied. To move it to the left, adjust the lower slider. Once you've finished with this floor, move on to the next one. Return to the ground floor. The program automatically saves your progress every time you switch to a different plan. Add the cantilever beam to support the wall extending 1.1 meters. If you need to exit before finishing, you can safely do so. When you reopen the program, go to the 3D model, and you'll find your previously saved work intact. After completing the input, proceed to the stair landing level. Since this level has walls taller than other floors, the wall height needs to be recalculated. Use the roof elevation at plus 7.0 meters and subtract the stair landing elevation at plus 2.2 meters, resulting in 4.8 meters. Then, subtract the beam depth of approximately 0.3 meters, leaving 4.5 meters. Multiply this height by the wall load of 200 kilograms per square meter to calculate the wall weight as 900 kilograms per meter. Once you've finished with this floor, move on to the next one. When returning to the plan view, the cantilever slab may disappear. If this happens, redraw it. Once the floor slabs for all levels have been defined, check that every level is marked as complete. If any level is not marked as complete, revisit it and ensure the slabs are fully defined. After confirming that all levels are marked as complete, click the button to generate the staircase. From the staircase plan, the width of the staircase is 1.2 meters. And it is a standard staircase. The live load is set to 200 kilograms per square meter, while the dead load includes only the tile weight of 50 kilograms per square meter. The self-weight of the staircase will be considered separately during the design process and is not included here. Click the Select Stair Zone button. Mark the area where the staircase will be constructed. Choose the desired staircase type. Next, we will demonstrate how to modify and customize different types of staircases. Go to the plan view. Adjust the landing dimensions and staircase width by referring to the section view, and modify the landing spans L1 and L2 accordingly. Create another staircase by following the same steps as the first one. To add supports, click the Add Support button. Select the floor to add the support to. Choose the support location, and then confirm. To remove a support, swipe left to delete it. The same method applies to deleting staircases. Next are the steps for design configuration, where we need to set the material strength and safety factors before proceeding. These settings are based on the chosen design method and the applicable standards. In this example, we will use the strength design method and apply the safety factor configuration from method 2. The first field is the safety factor for increasing the applied loads. Next is the material strength used for design. The FC field represents the compressive strength of concrete. If no certification documents for the concrete mix are available, refer to this table. For instance, 150 KSC is considered a very low compressive strength for concrete. While this improves safety in design, it can significantly increase construction costs. The FS field represents the yield strength of the reinforcement steel. For residential slabs, plain round bars are commonly used, with a yield strength of 2,400 KSC. In beams, there are two types of steel reinforcement: main reinforcement and stirrups. Stirrups are denoted as FV and are typically made of plain round bars with a yield strength of 2,400 KSC. Main reinforcement bars, on the other hand, should be deformed bars with a minimum yield strength of 3,000 KSC. In this example, we will use 3,000 KSC. DD refers to the concrete cover, which should be selected based on the table provided. For slabs, the concrete cover is 2 cm, and for beams, it is 3 cm. The deflection coefficient is used to verify the beam's deformation. The program will divide the beam span by this coefficient and compare it to the allowable deflection value. If the calculated value exceeds the limit, the program will provide a warning. Next, we will set up the analysis and design parameters for beams. The first option is beam analysis, and the second is grid analysis. Both methods allow you to choose between analyzing with moving live loads distributed based on influence lines or uniformly distributed loads over the entire length. Analysis based on influence lines provides more conservative results. Next is the selection of support types. The diagram illustrates the behavior of different support types. The structural response varies depending on the support configuration. We recommend analyzing the structure using both pin and fixed supports, with the fixed support percentage set at 50%. Following that is the option to consider torsion from the slab. It is recommended to include torsion in the calculation for enhanced safety. The design process offers 3 options. 1. Automatic selection of both beam sections and reinforcement. The program will select the beam dimensions and reinforcement automatically based on the analysis results. 2. Manual selection of beam sections while automating reinforcement design. Once selected, the program will display the list of beam groups. If no groups have been defined yet, click Add to create a new beam group. Assign a name to the group. Hide the list for easier configuration, and specify the section name, beam dimensions, and reinforcement bars. In the stirrup spacing field, specify the minimum allowable spacing. If the calculated spacing is less than this value, the program will switch to the next larger section. It is not necessary to arrange the beam sections in order of strength. The number of reinforcement bars will be based on the calculated requirements. If no suitable section matches the calculated reinforcement, the program will select the next larger section. If no larger sections are available, the program will display the calculated reinforcement requirements. For this setup, we will use a beam section of 20 by 40 cm with stirrups RB6, number 2 bars, or RB9, number 3 bars, both with a spacing of 10 cm. If the smaller stirrup spacing is too tight, switch to the next larger stirrup size for easier construction. After configuring, select the beam group you created. 3. Enhanced design options for beam sections and reinforcement placement. This option builds on the first two and allows you to prevent beam designs where reinforcement is subjected to compressive forces. You can define the location where this is applied, mid-span, near the supports, or both. If compression reinforcement is required, the program will switch to a larger section to ensure the concrete resists all compressive forces. This option is ideal for precast beam analysis, but for general construction, we recommend using the second option as it is more cost-effective. Next is the beam modification process, which has two options. 1. If any beam in a specific group needs a larger section, all beams in that group will be modified. 2. If only one beam requires a larger section, only that beam will be modified. Click OK to confirm the settings. The program is currently designing beams, slabs, and staircases, as well as handling structural modifications. Any adjustments to the structure will be made after completing the design. This page shows the combined floor plans. In this example, we are using Pro Mode, which already includes elevation levels and wind loads, so no adjustments are necessary. We will demonstrate a case where additional plans need to be added, or if Pro Mode is not being used. In such cases, this method of combining floor plans is required. To add a plan, click the plus button, select the plan, and input the elevation and wind loads. If the plans are misaligned, click the Move button, select a reference column, and drag it to the correct column position. To delete a plan, on iOS, swipe left. On Android, tap the trash can icon. To edit elevations or wind loads, click the Edit button. Next, we select wall positions. This step is optional, but selecting walls improves the accuracy of wind load distribution. To add walls, go to the plan, select the wall weights, and click Add Wall. Complete this for all floors. The next step is to apply additional loads to columns. This is for cases where additional loads are applied directly to columns. In this example, no such loads exist, but we will demonstrate the process. Select the plan where you want to apply the loads, click the Apply Load icon, select the column, and confirm. Next, to create the roof model, go to the roof icon. In this example, we will use a hip roof with a roof overhang of 1.1 meters. The purlin spacing can be obtained from the tile product specifications. In this case, we'll use a spacing of 0.35 meters for the purlins, and a common rafter spacing of 1 meter for the tile roof. Here, you'll find a button to select the steel section group, similar to the beam section group we configured earlier. Click on the Add button, then name the section group. The program will suggest a default section. If you don't use that section, you can delete it. On iOS, swipe left. On Android, select the section and click Delete. For this example, we'll add one section. Click on the Add button, select the section type, enter the section name, and specify the dimensions, A, B, and the spacing according to the section shape. Fy represents the yield strength, and Fu represents the ultimate tensile strength. Click OK. To edit, simply click on the section and make changes. For live load, use 50 kilograms per square meter based on the table, and for dead load, use the tile weight of 50 kilograms per square meter. If solar panels are installed, increase the weight to 100 kilograms per square meter. Alternatively, if the designer wants to add another 10 kilograms per square meter for the ceiling structure, that can be done as well. You don't need to enter the weight of the steel structure, the program will calculate it automatically. Next, click the Select Roof Zone button. Choose a reference point. Press and hold, then drag to define the zone. Once the position is set, release your finger and click OK. The roof will be created, and the program will automatically select the appropriate section. Click to edit the steel section. If the section doesn't pass, the steel profile will appear in red. To view the calculation results, click the eye icon. You'll see that the section doesn't pass because the deflection is too large. To fix this, 1. Use a larger steel section, or 2. Add a support. We'll use the second method and add a king post at the center of grid line 2. Go to the Edit Roof button. Hide the purlins and rafters. Then click on the king post. Click Add. A new king post will be created. Drag it to the desired position. Then release the mouse. In this example, the roof is relatively simple. So we'll proceed with the same settings used in the previous example, as it's the same type of roof. First, drag to the main roof. This roof has a very long rafter span, so we'll use a larger steel section. A recommendation is that if the horizontal span of the rafter exceeds 5 meters, we should add a stud beam to support the central part of the roof. First, determine the elevation of the stud beam by checking the column position. Try to align the new stud beam with the column axis to strengthen the structure. In this case, the appropriate distance is 4 meters from the rafter span. To calculate the stud beam elevation, multiply 4 meters by the tangent of the roof angle, 30 degrees. Then add the original stud beam elevation of 7.0 meters. This gives an elevation of 9.31 meters. Enter the elevation. Then drag to any point on the roof. Click OK. If the stud beam has excessive deflection, we will add a steel column to support the end of the beam. To modify the stud beam, double-click to change the mode, delete the existing stud beam, and then select a steel column and swipe up to place it. If we want the tie beam to rest on the new stud beam, we should delete the existing roof and create a new one. Next, create a subroof that will connect to the main roof. Slide to select a compatible roof type and confirm the selection. The purlins of the main roof will be trimmed to match the chosen roof shape. Now, let's demonstrate another roof type, a shed roof. We will use stud beam and metal sheeting as the roofing material. Start by creating the steel studs at an elevation of 7.0 meters and select concrete columns. Extend the columns to cover the entire stud beam location. Adjust the stud beam. Then create the concrete columns. The concrete column lines will appear in the design. Next, extend the stud beam by 0.5 meters. Then, create the roof. Choose the shed roof type. For a metal roof, the purlin spacing is typically 1 meter, and the rafter spacing ranges from 2 to 4 meters depending on the design. It's recommended to adjust the rafter placement to maximize the load transfer to the columns. In this example, we will use a rafter spacing of 3 meters along the beam direction. And set the roof pitch to 5 degrees. The dead load will be set to 15 kilograms per square meter for the shed roof. To ensure the roof load is transferred to the rafters, we will design the king post to carry the load of all the rafters. Turn off the visibility of the purlins. Remove the ridge. And create additional king posts. Position them directly over the columns. When we add additional rafter supports, we can reduce the size of the steel section to make it more efficient. If additional rafters are needed, select the rafter and press Add. Release the finger once the desired position is selected. To rotate a tie beam to another direction, select the tie beam. A rotate button will appear. Press the button and adjust the tie beam until it aligns with the desired orientation. This rafter is just for demonstration, so it can be deleted. Next step, design the column and foundation structure. The design method should be the same as for the beam design. For beam design, we used the strength method, so we will use the same method for the column design. In this example, I will use the same safety factor as in the middle column. The weight to soil multiplier is the coefficient used to convert the load factor multiplied by the safety factor back to the actual load, which will be used to calculate the number of piles and the size of the spread foundation. You'll notice that in the working stress design method field, the value is 1. Because the safety factor for the unit force method is 1, so no conversion is needed. Once set, click OK. The concrete strength will be set to 150 KSC as before. For Fy, we will use 3000 KSC. And for FV, the stirrup steel will be set at 2400 KSC. The density will be 2400 kilograms per square meter. In this example, the concrete cover will be according to the table. Column cover is 2 centimeters. Foundation cover is 5 centimeters. There are 2 foundation types to choose from: pile foundation and spread foundation. Set up the pile foundation. The pile we will use in this example is an I-shaped pile with a size of 22 centimeters. The bearing capacity of the pile depends on the surface area of the pile, the length of the pile, and the soil condition of each region. In this example, we don't have soil data, so we will use the table specifications to determine the bearing capacity of the pile. Start by calculating the variable p to calculate p for the I-section pile. Use the size of the pile multiplied by 4. Our pile size is 22 centimeters, which is 0.22 meters. Multiply by 4 to get 0.88 meters. From Table 21, the bearing capacity of a pile with a surface area of 1 square meter is 17,300 p. So multiplying 17,300 by 0.88 gives 15,224. We will use 15,000 kilograms as the value. For the foundation depth of the pile, there is no specific requirement, so we will set it to minus 0.5 meters. Next, set up the spread foundation. The soil bearing capacity is calculated using the bearing capacity table when there is no soil survey available. For example, if the construction site is in compacted sandy soil, the bearing capacity is set to 10,000 kilograms per square meter. The distance is the measurement from the foundation to the level of plus 0.0 or the ground level. The specification requires that the spread foundation be buried in the soil by at least 1 meter. We will use 1 meter. Next, select the analysis method. The first option is beam analysis, which combines the loads from each floor and analyzes the moment for each floor as a beam. The second option is 3D structural analysis, which considers the combined loads. The critical forces in the beams obtained from 3D analysis will be updated and redesigned accordingly. If the strength design method is used, it is recommended to perform a 3D analysis or both analyses. Set the combined loads. We will use the middle option as usual. To delete a load, swipe left on iOS or press the trash icon on Android. Once the values are entered, proceed to wind load settings. Select the wind direction. If no data is available, analyze the wind load in all directions. For seismic settings, if the structure is located in a non-seismic zone, input a seismic response coefficient of 0 or do not select any seismic direction. For support settings, it is recommended to use the same settings as in beam analysis, with pinned and 50% fixed supports. Confirm your selections. Go to the column group in the structure. Double-click to view each floor individually. Switch to multi-select mode. Select all columns on the current floor. Then swipe up to view other floors and select all columns. Ground columns should have a minimum thickness of 25 centimeters. Change the size to 25 centimeters for ground columns. For the other floors, set the column size to 20 centimeters. Meeting the minimum cross-section requirement. Update all reinforcement to DB16. The software will automatically calculate the required quantity of reinforcement. Increasing the size of ground columns reduces punching shear on the foundation, allowing for a thinner foundation. The software currently specifies a thickness of 50 centimeters. We'll reduce it to 40 centimeters, ensuring it doesn't go below 35 centimeters as per the design requirements. If the design fails to meet the criteria, the thickness cannot be reduced. Update the reinforcement to DB16 throughout. Next, We will proceed to revise the beams. Start by navigating to the beam group page to get an overview. Then, edit the cross-sections that appear inappropriate. Once the group edits are complete, move on to adjusting the cross-sections individually. Increase the reinforcement bars as needed to align with the group for better consistency. This simplifies the structural design and reduces the chance of errors during construction. For beam groups with only a few members, try to merge them with nearby groups. For example, in this case, there is a single beam in its group, but it is close to the BT1 beam group. We will change the stirrups to RB9 so it can join the BT1 group. The button below provides access to the critical data for the selected beam and the calculation summary. Inspect the reinforcement details. Beams not highlighted in blue indicate that the program is flagging them for review. Enter the edit mode and select the beams highlighted in red. The program will explain the issue and recommend a solution. For example, in this case, the deflection exceeds the allowable limit. The solution is to either increase the beam size or enhance the concrete strength. Increasing the beam depth is the most effective solution for deflection issues. We'll adjust the depth from 40 cm to 50 cm and also modify the size of the connected beams. You'll notice that the warning disappears. Check the cantilever span. Once done, return to the model. Revise the second floor beams. If the reinforcement seems unusual or doesn't match the defined settings, rerun the automatic design. This is because the 3D structural analysis occurs after the initial design, and the system might adjust the reinforcement based on updated values. Rerunning the automatic design ensures the grouping reflects the critical results from the 3D analysis, making the grouping more consistent with the defined parameters. The reinforcement calculation system operates automatically. When additional loads are applied, the system increases the reinforcement accordingly. For example, consider a beam cross-section with 2 top bars and 2 bottom bars. If we apply a point load of 5,000 kilograms, you'll see the reinforcement increase to 3 bars at both the top and bottom. This reinforcement system is designed to ensure safety. If the tensile reinforcement increases to a point where concrete failure might occur before the reinforcement yields, The program will automatically increase the compressive reinforcement to prevent such scenarios. Additionally, it will not reduce the reinforcement below the calculated minimum values. To review the slab calculations, select the Slab Selection button. This will take you to the slab selection mode. Click on the slab to edit its cross-section and reinforcement. Revise all beams on every floor. Edit the staircase. If the thickness is set too low and the reinforcement bars don't appear, it means the thickness is insufficient, which may lead to concrete failure before the reinforcement bars are activated. This is very dangerous. To fix this, increase the thickness of the staircase. Next, review the building's structural group. If you're satisfied with the structural group, you can export the calculation list by clicking the PDF button. Or, if you are on the model page, go to the Calculation List button. The difference between the 2D and 3D calculation lists is that the 3D version takes longer to export and uses more memory during analysis, which can sometimes lead to the program crashing due to exceeding the allocated memory. To address this, a 2D analysis option has been introduced. The process involves converting the 3D analysis graphs into 2D. Add a caption below the image. In this example, the caption will say, Calculation List. The text in the left corner should include your name. We will export the calculation list all together in one document. After closing the export list, check if any changes need to be made. Once everything looks good, click the PDF button again and choose your next action. You will have options to share via Wi-Fi, print, or save to your device. Alternatively, you can sign the document digitally by editing the file. The exported file example will be shared on our Facebook page, AutoRC Analysis and Design, with a link provided in the description. Next, let's look at the rebar details and the bar cut list. This list contains an excessive amount of reinforcement. We can limit the visibility to make it easier to view. To hide some parts, enable the beam selection mode. Open the list, and view the reinforcement in the list. The reinforcement locations will be shown on the model. Go to the settings, and we'll display the effects of various settings, which will also affect the quantities in the BOQ. These settings can also be adjusted on the BOQ page. First, for epoxy coating, select the uncoated option. For concrete, if we are using lightweight concrete, select this option as lightweight concrete has a lower bonding strength with reinforcement, which results in longer embedment lengths. Next, let's configure the beam stirrup reinforcement. The first option is the economical stirrup reinforcement in areas with low shear, where reinforcement will be added according to the minimum stirrup requirements. In areas with high shear, the reinforcement will follow the calculated values. The second option adds reinforcement according to the calculated values along the entire beam length. The third option bases the stirrup spacing on the beam group settings, but if the calculated value is shorter, the shorter value will be used instead. You can select the beam group using the button below. Next, configure the beam reinforcement. The first option uses standard ACI guidelines for the reinforcement stop lengths, which results in using less reinforcement than the second option, where reinforcement is continuous along the entire length of the beam with no stops. For floor reinforcement stops, they will stop at 1/3 of the longest span length, L. In the case of precast floors, RB9 rebar is typically used at 40 cm intervals for the dowels. For column stirrup reinforcement, it follows the same configuration as beams. Now, let's look at the three export options. 1. The first option exports based on the selected structure. You need to select a structure first. For example, if a beam is selected, the export will show the reinforcement details for that beam. 2. The second option is the bar cut list, which will export a list of the cut bars, showing the quantity and length of the bars. 3. The third option is the shop drawing or construction drawing, which uses A3 paper size to display reinforcement details in 3D and show section views along with the structural positions. For structural steel, it will indicate the cutting length to fit perfectly with other steel members. You can double-click and swipe up or down to view each floor individually. Next, go to the BOQ, Bill of Quantities, which covers material quantities and pricing for the structural work. You can view the structural quantities calculated by the program by clicking on the corresponding list item. Enter the pricing settings and specify the currency unit. You can create a pricing group for cost calculation. Select the pricing group and click Add. Name the group. The program will provide default values, which can be deleted. On iOS, swipe left. On Android, click the trashcan icon. To add a new item, click the Add button. Select the calculation type. For area calculations, you can choose the sides to include in the calculation. For volume, which refers to the amount of concrete, it's recommended to add a 10% allowance by setting the coefficient to 1.1. This means the calculated volume for pricing will be 10% more than the actual volume. For example, if the actual volume is 100, the pricing calculation will use 110. Set the labor cost as needed. To edit an item, click on the list and make the necessary adjustments. For calculating the length of steel sections, you can set prices based on the steel types you have defined. For reinforcement steel, you can choose to calculate based on weight or length, and adjust the price for each type of reinforcement steel. To export the BOQ list, click the PDF button. The price will be calculated based on the settings you've defined. You can review the calculated column list and structural analysis items. Save the model.